Welcome back, ladies and gentlemen. In kinematics, we spent a bunch of time studying the way things move, right? Kina, the kinesthesiology, that starting prefix to the word means motion, and matics is, of course, study. So kinematics is the study of motion. Dynamics is going to be the study of forces, and broadly speaking, how they cause motion. Now, a fairly smart chap called Newton was the one who figured out these three laws. Now, admittedly, his original calculations, his original work was a lot more complicated than what you're going to see in this unit. And that's because over the centuries, literal centuries, that someone has managed to first come up with this, we've had the ability to improve it, to refine it, to make it simpler. This unit is very different than kinematics in a lot of ways. There are actually only two formulas in the entire unit, and they're very simple. The rest of the challenge comes from being able to add properly. And unfortunately, a lot of people struggle with that. They find it difficult to add multiple numbers together. And I know this sounds like I'm pulling your leg, but no, that is literally the problem that we're going to have here, is adding things properly. So first things first, Newton's three laws. Newton's three laws, they've got very formal definitions. They're written in your notes. I'm going to give you some informal definitions. And the advantage of informal definitions is that they are a little easier to remember in a lot of cases. So the three laws, of course, are first, second, third. And when it comes to what they are, the first law is inertia. It's literally that, the term inertia. If you know what the word inertia means, then you understand what the first law is. And that's it. That's all you would need. Now, most people don't know what inertia means, so a little bit of an explanation here. Things only move if you push them. That is what inertia means. So if you understand that idea, I don't have to explain it to you. I don't have to explain every single time things only move if you push them, if you understand the idea of inertia, because the word inertia defines the rest of this. It's just like how if I tell you that thing over there is fast, I don't have to explain to you what fast means every time, because you understand what the word fast already means. That's sort of how language works. If you understand the underlying concept of a word, then you don't need a description. If you don't understand the underlying concept, then you do. And there's nothing wrong with wanting things explained. But if you understand stuff, you can move quicker, which is often a helpful example. Second law is basically represented as a formula, F equals ma. And this is our first of two formulas in this unit. So, we're halfway there already. F equals ma. F equals ma was not how Newton originally calculated it, and we'll see that when we get to momentum and energy in two more units. So F equals ma basically forces or pushes create acceleration. That's it. That's what this is. If I have an object and it has mass, so it physically exists in space, such as my handy box, and I apply a force to make it move, that's it. The first law basically tells you how things sort of behave. The second law tells you the exact mechanism by which the first law unfolds. First law says, if you don't push it, it doesn't move. Second law says, if you push it and you push it this much, it will move that much. So this one is more without numbers, right? So it's qualitative, as they call it. This is quantitative. This has numbers to it. Quan, in this case, meaning like quantity. So we've got a third law. Well, what's the third law? Well, the third law is just recoil. That's it. You've heard of recoil. And this is a term in which probably some of you are now going, oh, wait, I know what that one is. Yeah, because it's a fairly common one used in everyday conversation. It's the basic idea that when you push something, it pushes back. Put another way, right? If I touch the marker touches me. Now, usually when I'm explaining recoil in class, I will point out that recoil is the reason why, if you, not that you of course would do this, were to turn around and hit your friend in the face, your hand hurts. Right? You hit them, but because you hit them, it's almost like they hit you. It's just you hit them with a hand and they hit you with a face. That's the reason why your hand hurts. Usually, at this point, at least 6 people have turned around and hit their friend. And then their friend has hit them back. Unfortunately, you guys are a little bit farther away from each other, so I doubt that's happened, but, better times. Anyway, those are Newton's 3 laws, and everything that we're going to deal with boils down to these in the end. Like, everything. If you understand these, they're the foundation. Now, that is why the Newton's inquiry exists in the starting parts of the book, so make sure you give it a try. Other than understanding the 3 laws, the other thing we need to do is understand diagrams, how to draw. I've mentioned before how drawings are very important in this particular unit, in previous units. Well, they're even more important in this unit, to the point where, generally speaking, diagrams would be part of the test. You'd have to actually draw a diagram, I have to see it, and you'd get marks for it. Now, with our new digital component, I will probably not request some diagrams, but it's still good if you know how to draw them. So, clearing off some board space, diagrams are called free body diagrams. Now, free body in this case means just like an object, just anywhere in space. So this eraser, this is now a free body. Boom, it's right there. Free means that there's nothing else sort of interacting with it or interfering. Now, at the moment, I'm interfering with this. I'm applying a force, pushing this into the board, which is why it's able to stay there. If I let go, it falls on the floor. This would officially not be a free body, but physicists will try to be lazy if they can swing it. If. And as a result, they'll just assume that there's just, objects anywhere. Now, you guys have seen my drawing ability, so you kind of already know I can't draw, and that's pretty normal for physicists overall. I didn't take art class, which is why, generally speaking, physics diagrams are going to be pretty simple. Generally speaking, you get boxes, or you get circles. So here it is, a box. This is our body, and it is free. Now I'm going to put some forces on this free body. Now, there are 4 different forces that we're going to deal with on a regular, consistent basis in this unit. Not every question will have all 4 forces. Not every question will have the same 2 forces. Not all the forces will be on the same side of the object. They could be different. But there are certain things that we know. For example, that eraser that fell on the floor, what pulled it down? We know that. At least I hope so. If you don't know that, then I'm about to amaze you, because there's this thing called gravity. And you may have noticed that it is a force of gravity. So, here we go. Fg. You may remember from Newton's second law that we had F for force. Well, Fg is the force of gravity. We also sometimes call it the gravitational force. That's if we don't want an of in there and we want to use bigger words. They really just mean the same thing. It doesn't matter. Now, at the moment, my eraser here that I didn't drop on the floor is sitting on this table. Yeah, you can't quite see it. Can you raise it up a little higher there? There we go. Welcome back. Small interruption. Where was I? Force of gravity. Now, yes. The eraser here is sitting up above. So is the case for the markers, and the eraser that fell on the floor, it stopped, of course, right? Like it hit the floor and then it didn't keep going. I didn't bore a hole all the way to the center of the earth down there, right? Something had to stop it. And remember Newton's laws. If something is moving, that means I applied a force. So in order for it to stop, I have to apply a force. Well, what force stopped it? The force of the floor, I guess? But force of floor is a little vague. Also, it's not fancy enough as far as mathematicians and physicists are concerned. I bring up math for a reason. So they actually do have a force that opposes gravity for most objects sitting on surfaces. And I'm going to draw that one here in orange. And its symbol is Fn. And this is force normal, or the normal force. And why is it normal? Math. I mentioned math. There's where it's from. It is a mathematical term. Normal means perpendicular to a surface. Big words there. Surface, of course, is any object. So, here's a eraser, right? The eraser, this is a surface. We'll make it easier to see. This is an eraser. The top of this eraser is a surface, right? I can take something, and I can put it down on top, and it'll stay there, provided I can balance it. Well, perpendicular means right angles. So something that is perpendicular to a surface means it points up. And you'll see that it's a nice right angle between the marker and the surface, right? This would be this would be not a right angle. This is definitely not a right angle. This is a right angle. And if I rotate the surface, it is still perpendicular to the surface. So for objects that we put on top of, shelves and things, the force normal points straight up. Because gravity points down and it's trying to pull it down, and the table is pushing up against gravity. But earlier on, I did this little trick. Where's the surface? Well, that'd be the whiteboard. Whiteboard's a surface. And the force is normal to the surface. The force will be perpendicular to the surface. So that means that the force, normal, would be that way, coming out of the board towards you and the camera. Well, that's weird. And that's the part of this that sort of tends to confound people, because you tell somebody that the orange one is always up, and they go, sweet, I can understand that. That is very simple. You tell somebody that the orange one always points perpendicular to the surface, and they'll go, can that always be up? That would be much easier for me. Why do I have to think about what perpendicular means or what a surface is in this context? That's annoying. And unfortunately, that's the case. So FG will generally point down towards the surface of the Earth, or I should say the center of the Earth. Fn will generally point perpendicular to the surface. Yay. What else do we have? Well, I said in Newton's laws that things only move if you push them. So what happens if I give something a push? Well, in order to push something, we also use a force, and we call it Fa, or force applied. Force applied is one of many terms that we're going to see. Fa, force applied, usually by a person or a machine, like a car or something. There's also going to be Ft. Ft can be considered the force of tension or thrust. Tension is the fancy name we give to a string. So if I grab this very convenient elastic band here, assuming that it will come off. Looks like this is a total mess. Here is an elastic band, right? This elastic band is currently pretty loose. Hangs there, nothing fancy. If I apply a force with some gravity pulling down, you see that it, of course, becomes tense. It becomes tight, taut, as the past tense would go. This is a force of tension. Now, realistically, it's a force applied. I am applying a force down. Boom. Gravity's also helped me out. But we give it a fancy name, and generally what we're saying is that forces of tension are forces of strings. That's the key. So there it is, force of tension. Force of thrust is the fancy name that we give to forces that are pushing. So a rocket ship, thrust is pushing it up into the air, stuff like that. But at the end of the day, they're all basically forces applied. They're just in different contexts, different situations. Now, I got one more color, and I got one more force. And that last force is one that you're familiar with. It's one that you deal with in your everyday life all the time. It is the force of friction. Now, the force of friction, I'm using a weird symbol for it there for one, and the force of friction is, of course, very important. Everything we do, all the time. Without it, we wouldn't be able to walk or move or hold on to markers that just fell on the floor. The force of friction is why two things come apart and go together. So, why do I use that weird symbol? You're going to see. There are two formulas I said in this unit. F equals ma, or as one of my enterprising students once declared, FMA. And then there is force of friction. And one of the symbols in the force of friction is that weird little symbol that I drew there underneath F. So I'm telling you what the symbol is as part of the original force. That little symbol, by the way, is a Greek letter. We've actually got a lot of Greek letters in physics, you may have noticed. But, what Greek letter? That is the Greek letter mu, like what a cow does. So, this is mu. Now, the way you draw it is basically you draw a U, and then you draw a little curly bit that comes down like so. That's it. If you get some more practice, you can do it all in one go, but that's how you set it up. If you don't want to use mu for your force of friction, you can. You can use force of friction like this. I've also seen force of friction like this. There are lots and lots of options. I'm going to use F mu, however. So there you go. There are the forces, and you'll see that there are some variations in what they can do, and I've already mentioned that they can have different sort of positions. We've already talked about how Fg will generally point to the surface of the center of the Earth, and how Fn will point perpendicular to a surface. Fa can be pointed in any direction at all, right? Like in this diagram, I pointed it to the right, but I could just as easily push something left. I could just as easily lift it up. I could just as easily throw it down. All of those are options. I can push in any direction. Friction, its general tendency is that it will oppose any motion. Whatever something is trying to do, if something is trying to move, friction will try to stop it. Friction is sort of the, wet blanket. It's the party pooper. It doesn't want to have a good time. It wants everyone just to sit still and do nothing. So, very topical, I guess. So there you have it. Those are the four forces. They can be in any number or direction. But I had said a bunch about adding. Well, what do I mean about adding? Well, let's take a look. Because this whole unit is about being able to add. That's the thing. You need to be able to add. And people have a hard time with that. Adding is a challenging thing. So let's see some examples of what this might look like. Very simple one here, right? Think about all we know about the different Newton's laws. I've got an object. It's just sitting there. I'm going to put it on top of a table. There you go. There's a table. Very complicated, very technical, I know. And I'm going to apply some forces. Okay? So I'm going to apply a force applied. I'm going to push like so. And I'm going to say that this is 100 newtons of force. You know you've done a good job in physics or science in general when they name something after you. So in this case, it's named after Sir Isaac Newton, who figured this stuff out. We'll talk about that just a second here. So we've got this 200 newtons, and it's on a table, and, friction opposes motion. So right now, if I do nothing else, which way is it moving? And everyone looks at that and they go, okay, well, it's going that way. It's going right. Okay, great. So if the object is currently moving right, and there is friction, friction will go left. Now, the question is, what's going to happen with different amounts of force? Well, okay, if I make this 100 newtons of force, what is my total? What is my net force? There's a term, net force. Net is another math term, and it means the sum, or add everything. The symbol for net force is this one here. Or at least that's usually how I end up drawing it. Technically, you should use a capital sigma, another Greek letter with an F, but I get a little lazy. I just do a little bit of a lowercase sigma, keeps it easy. So this is called the net force, which is just add all the forces. So if I add all these forces, well, let's look at this. These are vectors. We know how to do one-dimensional vector addition. This is 100 going right. This is 100 going left. If I add those two up, I just get 0, right? Because this is going to be the sum of forces is equal to the force applied and the force of friction. And I'm going to add them because that's what sum means. Then I write down the numbers. This is plus 100. This one is minus 100. And I add them. Well, in total, this will be 0. So there we go. This is how we do a dynamics problem. And that's kind of all there is to it, actually. Pretty much every dynamics problem is going to be this at the end of the day. You have to add everything. And, that's really hard because you've got to, figure out what things are going together. I know, you're looking at that going, how's that hard? We've done this a million times, right? That's just like 100 meters right, 100 meters left, I'm back at the start. Yeah, that's how it works. So this particular object, if the total force is 0, are we actually moving? That's a tricky one. Well, we did say that an object will stay still unless you push it. But I'm pushing it right, and friction is pushing it left at exactly the same force. So because the two forces are perfectly balanced, nothing happens. This is why, for example, I can't push on the wall and knock it down. No matter how hard I push, the wall pushes back. What force is the wall pushing back with? Well, there's only 4 options. Could be force applied, right? The wall is applying a force on me. But generally we use force applied for people or machines, and the wall is neither. It could be force of gravity, I guess, except that force of gravity points towards the center of the Earth. And unless you think I'm doing some pretty crazy special effects, that's not the center of the Earth. The center of the Earth is this way. Could be force of friction, I guess, except force of friction opposes motion. So if I'm trying to push this way, force of friction would be that way. So, at least that's the right direction, but I'm not really moving very much. Could be force normal. Right? It's perpendicular to the surface. It's pointing towards me. I'm pushing in, so yeah, I guess it could be force normal. So, tricky. It would be force normal in this case. So yeah, in this particular situation, there would be no motion because the two forces are in balance. If there is a balance of force, nothing happens. Okay, but what happens? We change it up, right? I come over here, I erase that 2, that 1 I should say, and I make it a 2. Well, now how does this change the equation? Well, actually, it changed the equation not at all. All right, I'm being semantic. It doesn't change the formula in any way. It just changes the number I put into it. When I want to do the sum of forces, the net force, it's still just Fa plus F mu. Force of friction, force applied. The only difference is, now this one is 200. Ta-da! Well, we know how to do that math. 200 minus 100. Gee, I wonder what the answer is. Very complicated, Mr. C. 100. Is that it? We done? No, we need to know the direction. It is a vector. 100 plus. Oh, we should put some units on there too. N. So what does that mean? Well, I've got 100 newtons of force. That means that now I do have motion, and it is motion to the right. And remember, Newton's second law says that if I have force and I have motion, I have acceleration. So this object will actually be speeding up. It'll be getting faster. In kinematics, we talked about acceleration a whole bunch, but we kind of just sort of assumed acceleration was just there. We just say, oh yeah, there's an acceleration. The question would just say, hey, there's an acceleration of 20. And you'd be like, okay, sure, I'll work with that. This is where the acceleration comes from. That's kind of what we're doing here. It's like we're going one step deeper into the problems. Instead of me just telling you, acceleration is 9.8, I'm telling you, how much is the acceleration? Can you figure it out? Can you work it out? Can you calculate it based on the forces involved? So there we go. We're digging deeper into the knowledge. That's an object going left and right. What happens if we change things up? Right? Let's go up and down. Up and down's fun. Can be, anyway. Same thing. I'm going to have an object in space. There it is. Very fancy looking. And then I'm going to have that object on a surface, let's say. Right? Just going to put it on a table. There's our table. Very fancy. Well, if an object is sitting on a table, what forces are there? I'm not touching it in any way, right? No one's touching it, so there's no force applied. And it's not moving, so there's no force of friction. But it's on Earth, so there's a force of gravity. And generally speaking, as I've said, force of gravity points everything towards the center of the Earth. So, Fg. For 90% of the problems that we're dealing with, Fg will point down. Not all of the problems, unfortunately, which is going to result in this. People are going to take shortcuts. They're going to go, okay, Fg always points down. I'll just remember that and I'll just use it every time. And then later on, they'll get a problem where things are a little more complicated and Fg doesn't point down, and then they'll go, oh, right. Forgot that. Oops. -1. It happens. But for this particular moment, Fg points down, right? I've got this object here sitting on this counter. Gravity's pulling it down, but it is not currently moving, right? It's not currently going down. That means that something has to be balancing this force. As we saw earlier, if the sum of forces is 0, then the object doesn't move. Well, what is it? Could be friction. Friction does stop motion, but friction also tends to sort of be about the contact between two surfaces. So friction would be tricky because friction wouldn't necessarily work down or up. It would probably try to work left and right here. Right? I mean, you kind of know that, right? If I've got an object and I try to push it left and right, it's hard because friction tries to stop it. So obviously that just leaves us with our last color. Fn. Force normal, perpendicular to the surface. Force normal is just the name we give to the force caused by a surface, in this case a table. Right? So the table basically works as a very primitive anti-gravity device. Cancels out gravity, keeps it from falling. Now, if this object is not moving, that means some pretty critical things, right? And this is what we're going to see with a lot of these questions, is that they'll give you a problem and they'll just tell you the object is not moving. The object is at rest is one way that we could say that. Well, if the object is at rest, this tells you something about the various forces. Based on what we just saw with this problem over here, if the object is at rest, the forces must be balanced. So whatever the number is for the down force, the up force has to be the same, right? If the down force is bigger, well, that means that gravity's going to win. That means that slowly but surely the table will collapse underneath it. And if the up force is bigger, well, that means that the object will float, I guess. And unfortunately, tables are primitive anti-gravity devices. They are not sophisticated ones, so they don't make things fly. If one of you has developed a made a sophisticated anti-gravity device, feel free to let us know in the comments. Now, because these two numbers are the same, that means that if I tell you that this one is, say, 20 newtons, the other one also is 20 newtons. But now, a couple people are probably going, wait. You always told us in the last unit that gravity is 9.8. Why is it 20? Could we just use that? Could we just say 9.8? And yes, in the previous unit, gravity, or at least a piece of the gravitational puzzle, was 9.8. Specifically, gravitational acceleration. We're dealing with forces. Forces and accelerations are different. So making this 9.8 would, kind of be like, well, I'm going to use a phone number. I'm going to call someone using a phone number. So I'm just going to type in a bunch of random letters. They're symbols. They mean things, but they mean different things. Gravitational acceleration. Acceleration. Where does acceleration come up in this unit? When did we see an acceleration? It just showed up just a little bit earlier. Remember? Newton's second law. F equals ma. That a is acceleration. So what happens if I wanted to rewrite Newton's second law to talk about gravity? Then I would get Fg equals, well, mg. What's g? Why? G's 9.8. There's where the 9.8 comes in. Crazy, right? This is why Newton's second law is such a big deal. This is why Newton got stuff named after him. F equals ma works for all forces everywhere in the universe. Every force, no matter how complicated or sophisticated, can be described by that simple equation. And that equation is as simple as 2 times 3 makes 6. Now, does that mean this equation works for absolutely every situation? No, unfortunately not. Sometimes you don't know what the mass is or what the acceleration is. So sometimes you got to do a little bit more work to figure things out. But yeah, this equation works anywhere. So any of these forces that we've talked about can be represented by this equation. I could write, for example, Fn equals ma. Over here, I could write Fa equals ma. Now, admittedly, only Fg has an acceleration due to gravity that we already know. Now, to be fair, right, like Fg equals m times g, g is only 9.8 on the surface of the Earth. If I were to put you on Mars or the International Space Station, you'd have a different g. But since, barring some of you guys becoming super cool astronauts, most of you guys, like 99.99% of you, will spend your entire lives on Earth. This is just 9.8. And that's it. We're done. Now, can we do something more? Can we take it a little bit further? Yes. Yes, we can. Because there are a few peculiar situations when it comes to forces. Inertia does not just tell us about something that is not moving trying to move. Inertia technically talks about stuff that hasn't started moving yet. Or sorry, stuff that has already been in motion but may want to stop. Put another way, again, pretty much all of us are on Earth, barring some alien watching this video. And as a result of us all being on Earth, we all hopefully know that the Earth goes around the Sun, and the Earth continues to go around the Sun, and yet there's no rocket ships attached to the Earth to make it go around the Sun. Something is causing it to continue moving. That is inertia. The Earth got kicked into motion way back in the dawn of time. Well, maybe a little bit after that, to be honest. The Earth isn't that old. Compared to the sum total of the universe, that is. Total aside here. See, this is an aside that like you guys would get in class. Astronomy aside. You know how we have gold on Earth? Right? Pretty fancy stuff. Well, gold can only come about if a star goes supernova. Yeah? Gold is made from dead stars. So the fact that we have gold on Earth means that at some point, a star went kaboom, and then the pieces that were left over were turned into our star, the sun, and the Earth itself. So we're not even a really old star or a really old planet. We're sort of a younger one. Now, in this case, we're talking about astronomy, so young in this case still means billions and billions and billions of years, but it's younger. So, we're doing pretty good for our age, is what I'm saying. Okay, back to physics. So, inertia also includes stopping things that are already moving. What do I mean by that? All right, so we've got here a box, okay? And this box is sitting here, and it's moving this way, moving right. Right. So this could be the Earth, right? The Earth goes around the sun. It goes around the sun the same way all the time. It never stops. It just keeps going and going and going. So let's say this thing is moving to the right with an initial velocity of 10 meters per second. Well, in order for us to stop this thing, we know what we have to do from kinematics. In order to stop this, we have to make this final velocity 0. And if the initial velocity is right, we know from kinematics that the acceleration has to oppose it. So it has to be left. So there has to be some kind of acceleration that is left. So Vf equals 0. Now, if this was a kinematics question, we'd be done there. I'd be like, okay, great, you guys figured it out. But this isn't. This is dynamics. So what's creating that acceleration? How do we make that? We need a force. Okay. Well, maybe I want to stop this object that's moving. Maybe this object is a train, right? Maybe this object, we make this a little fancier here. Maybe this object is a train. Okay, we'll put a little conductor here. He's going to have a hat. And there's the rest of the train over here. The windows in the train tracks. There we go. And there we go. And maybe someday down the tracks there's some unfortunate little cat. And the cat is sitting on the train tracks. It looks like I gave him horns more than ears, but you know what? We'll work with it. There's a cat down on the train tracks, and I got to stop it. Well, there's a few different ways, obviously. Under normal circumstances, the train would hit the brakes. But it takes a while for the brakes to slow the train down. Far too long for it to stop from hitting that cat. Right? Because the train is really big. It's got a lot of force. It's got a lot of inertia. making it stop will take an awful lot. So maybe we need to get Superman to come in here, right? He'll fly down, he'll get in front of the train, he'll push it, cape, there we go. So he's going to push the train, right? He's going to save that kitten, because that's what Superman does. Even if it's an evil cat with horns, Superman saves people. So he's applying a force. He's adding extra onto whatever the brakes can do in order to stop this thing. So in this particular case, right, if I want to stop it, I'm going to apply a force backwards to make this stop. So this context would be the object slowing down. All right. It's pretty fair. I mean, obviously I got real technical here. I got all sorts of fancy drawings and such, but, at the end of the day, it's pretty obvious. The object was moving right, positive velocity. If I want the velocity to go to 0, the acceleration has to be left. We know that. We've done that for like 3 units now. So if I set up a much simpler problem, like so, object is still moving right with 10 meters per second. And then I apply a force going this way. What's going to happen? Right? We've got a force to the right. We've got force to the right. We've got a velocity to the right. Well, the force will create an acceleration. So it will have an acceleration going right, velocity going right. So this object will speed up. Ta-da. Now how to mess with everybody. What's going on? I added another force. It's force of friction now. What does that do? How does that change things? What are the options? Okay, well, option 1 is that the force applied and the force of friction. The first option is that in this case, the force applied could be bigger. That's the math symbol for greater than, right? So this one here would be a bigger number than that one there. That's what I'm saying. Okay, so that's option 1. Call that 1. Option 2, come on, you guys know this. You've been in math class for how many years? Second option is that the force applied and the force of friction could be the same. And option 3, of course, is our final part of the puzzle, where the force of friction is bigger. Let's put some space here. So those are our 3 options. Okay, so the object is already moving. Moving to the right. Moving to the right, and I've got 2 forces. This entire unit's about adding. Remember what I said. Okay, I have no numbers for this. So this is just very conceptual right now. You could put numbers in if you want, right? You could just say, okay, FA is going to be 10, and F mu will be 5, for example, right? So this one could be 10, this one could be 5. That means this one is smaller than this one. So if this one is bigger, when I add the forces up, the forces are overall pointing right. So if I do that with some math symbols, the sum of all forces, right, everything added up, will equal to FA, F mu, well, that means the sum of all forces, if I use those numbers that I just made up, this will be 10, this will be negative 5, because it's going the other way, and then we're going to get positive 5. So if I get in positive 5 right here, What does that mean for what's going to happen here? Well, in that case, I've got a force going to the right. I've got a velocity going to the right. Force to the right, velocity to the right, object will speed up. So option 1 here is faster. Option 3 will be the opposite, right? Because if I do option 3, that means this would be 5 and this would be 10. I'd flip them. Remember, I made up 10 and 5 just off the top of my head. The only thing we know is, bigger than, less than. So that means this one here would be slower, or slowing down, I should say. Speeding up, slowing down. Let's change that to speeding up. So we've got speeding up, we got slowing down. So what's that option in the middle? This is the tricky one. Same. Stays the same. Does that make sense? What? Yeah, usually this messes with people. The object was already moving. So a force creates an acceleration. That's what we say a force does. If the two forces are equal, that means that each force is creating exactly the same acceleration. If they have the same acceleration, that means they have no real effect on each other because the two accelerations are perfectly balanced. The net result is that it's just staying the same. No one side wins. That is inertia, right? Inertia says that objects will move in the direction of the unbalanced force. Put another way, objects will continue to do what they're already doing unless you push them. And your push has to beat anything else. Right? If I push on the wall and the wall's pushing back, the wall doesn't move unless I beat it. I'm not the Hulk, so it can. So in order for this push to have an effect, it has to be stronger than everything else. So the first option, where the force applied is bigger than the force of friction, the object will get faster. The second option, they will stay the same. There will be no change. It will stay at 10 meters per second the whole time. Constant velocity. And then the third one is slowing down. There we go. Those are our forces. So the next several pages in your book have some examples of drawing diagrams and other things like that. Give them a try. See what you can do. Your objective is to see if you can get a picture of what these things should look like. I will upload a few examples of those diagrams. All right, ladies and gentlemen, see you again very soon. We'll do another video talking about friction. Cheers.